We present UNIST, a model built on neural implicit representation that is able to learn both style-preserving content alteration and content-preserving style transfer between two unpaired domains of shapes using the same network architecture. Unpaired image-to-image translation has become one of the most extensively studied problems in computer vision community. Researchers are able to translate images into target domain with realistic details. However, when it comes to shape translation problem, especially unpaired shape-to-shape translation, there have been surprisingly much fewer works, and existing 3D shape translation methods are not able to produce high-quality translation results due to the nature of the point cloud representation. Here, we show two examples translated by Logan. In the first example, the input letter A with solid font is supposed to be translated into dotted font. In the second example, the input chair without armrest is supposed to be translated into with armrest. With our proposed method, we are able to produce cleaner shape boundaries using neural implicit representation and better handle topology changes during translation. To achieve this, we propose UNIST, a neural network that is built on autoencoding implicit fields rather than point clouds. Our translated results are cleaner, more natural, with well-preserved spatial features and fine local details, including smooth topology changes. The key idea of a work is to add position awareness through latent grid space and perform translation tasks on that space using generative adversarial network. In order to perform translation on the latent grid space, given 2D image or 3D voxel as input, we first use encoder to encode both source and target domains into the common latent grid space. Then, similar to training regular implicit network, for each query point, we first use bilinear interpolation to obtain the position-aware encoding vector and pass it to the implicit decoder to predict the inside and outside values of the input shape. This allows us to map shapes from both domains into the same latent space with structure of the input shapes encoded, and make the translation on the latent space possible. After autoencoding, we can perform translation on the latent grid space using generative adversarial network. Given shapes from source and target domains, we first use pre-trained encoder to extract the feature grid. The generator then has two tasks. It first translates the code of a source shape to that of the target shape. It also turns the code of a target shape into itself based on the feature preserving loss. Then discriminator first learns the true distribution from the code of the target shapes. It then tells whether a translated code of a source shape is real or not. During inference time, given the source shape, we use pre-trained encoder to obtain the feature grid, then use well-trained generator to translate the code of a source shape to that of the target shape. Finally, we use pre-trained implicit decoder to obtain the inside and outside values, and pass to marching cube to obtain the translated shape. Here, we show retrieval shapes from the training set of the target domain with respect to UNIST translation results based on different retrieval metrics. Our method is indeed aware of structured information embedded in the latent grid space. It generates shapes that are as similar to the input shapes as possible and alter the shapes to match the most distinctive features of the target domain, instead of simply retrieving from training shapes. We compare our method with other methods that can perform unpaired shape-to-shape translation on several 2D datasets. Our method not only produces cleaner translated shapes with significantly better visual quality, but also has better ability to handle topological changes such as the dots in the dotted fonts. Similarly, we compare our method with state-of-the-art method Logan on several 3D datasets to show the high-quality translated shapes produced by our method. We further sample same amount of points from meshes to direct compare with Logan since its output is in point cloud representation. Finally, we show the latent space interpolation of UNIST with and without using position-aware encoding. While UNIST with regular encoding generates clean shapes during interpolation due to the inherent nature of the implicit representation, adding position awareness leads to more natural shape translation with better preservation of spatial features and fine local details. The project page and source code of our work are available. Thank you for watching.